Hi, thanks so much for watching our presentation on time-invariant prefix-free source coding for MIMO LQG control. My name is Travis Cuvalier, and I'm a grad student in electrical and computer engineering at the University of Texas at Austin. This is joint work with my advisors, Professor Takashi Tanaka, who's in the aerospace engineering department here at UT, Professor Robert Heath Jr., who's in electrical and computer engineering at North Carolina State University. I'm first going to really quickly show you some notation. Most of it's pretty standard. The main thing is that random variables are bold and non-random variables are not bold. I use lowercase for vectors and uppercase for matrices. Unfortunately, this makes it hard to tell what's a scalar and what's a vector. When that's important, I'll let you know. The to norm with respect to a matrix is actually the max singular value norm. The other thing is that I use the latex script L to denote the length of binary strings. So sort of a general scenario we're thinking about is the following. Say we have some remote sensing platform, like a drone, that we're using to measure the state of some dynamical system that we're trying to control, like the vehicle platoon. The sensing platform might have onboard passive sensors that can be used to make measurements of the plant, and it might use those measurements to control the system of interest. In the picture, I'm imagining that the drone has like a really expensive camera, and it's using the camera measurements to send control inputs to the vehicle platoon. So in this scenario, the information the sensing platform gets is notionally free, but there's a cost in physical layer resources like time, bandwidth, and power for that downlink communication along the green dotted line. Our goal is to minimize the expenditure of those downlink phi resources while maintaining satisfactory control performance. I claim that we can do this by minimizing the required bit rate of that feedback length. So for like any fixed communication latency and reliability, minimizing the length of the messages that need to be conveyed from the drone to the platoon, subject to a constraint in the platoon's performance, minimizes the amount of physical layer resources required to solve the control task satisfactorily. So our goal is to minimize the required bit rate of that feedback length, subject to a constraint on the performance of the system being controlled. That's the platoon. This is like fundamentally a data compression problem, and in general, a lossy data compression problem with feedback. But the distortion we're going to be concerned with is the performance of the controlled system rather than something like perceptual quality. So we can sort of abstract this out into the following architecture. The plant is like the dynamics of the platoon that we're trying to control. Its state vector, like position and velocity, are measured by the remote sensor, who then conveys sensory information over an air-ground link back to the decoder controller. The decoder controller nominally controls an actuator co-located with the plant. We want to achieve some control performance, and we'd like to do that with a minimum bit rate over that air-to-ground channel, assuming it's ideal. We're going to assume that the plant is like a standard Gauss-Markov plant, and we're going to assume that we know all its parameters. For now, let's assume that the state space is m greater than one dimensional. We also have to make the technical assumption that AB is a stabilizable pair. We're going to measure the control performance via the LQG, or linear-quadratic-Gaussian cost, which you can see on the screen. The sensor and encoder is going to be able to measure the state of the plant. We're considering a fully observable case where no explicit noise is on the sensor readings. Then the sensor and encoder can use those measurements to produce a code word or a packet with a generally randomized causal encoder, PE. The code word, A sub t, is going to be a finite length binary string, which is assumed to be transmitted to a decoder controller reliably, that is, without delay and without error. The length of the string is allowed to vary across time per the encoder's policy. We're going to quantify the communication cost as the time average bit rate of the packets we convey to the encoder, from the encoder to the decoder. So I'm assuming that the channel is error-free. You can think of this cost as the minimum bit rate of reliable communication required to solve the control task. We'll usually require the code words to conform to a prefix constraint. These can allow the decoder controller, and more generally others in the network, to identify the end of transmission. I'm going to give you two examples of some prefix constraints that we can impose. The first constraint, which is weaker, says that essentially at any time t, the code words that can possibly be sent with non-zero probability must be prefix-free. This is sort of the Kober and Thomas definition. It allows anyone who knows the encoder policy at time t to identify the end of the code word by comparing what it receives with the marginal PMF of the code word A sub t. Note that this marginal PMF can change over time, so to identify the end of the code word at different times, the decoder or anyone else using the network might need to compare against different lists. So given this observation, you can also impose a stronger time-invariant prefix constraint that says that essentially the set of code words that can be transmitted at any time must be from a prefix-free code book. That way, you can identify the end of the code word by just comparing against a time-invariant list. So now, zooming back out, regardless of what prefix constraints we impose, given the code word it receives and the history, the controller can then randomly draw a control input, UT, which is input to the plant. Our goal is going to be to design encoder and decoder policies or strategies that minimize the communication costs subject to constraint on the control performance. We're going to cheat a little bit. We're going to allow the encoder and the decoder to share access to a common dither signal or shared randomness. The dither is going to be a sequence of random vectors that are IID uniform on an interval of size delta, and these vectors are going to be independent of the past. This is a trick that you often encounter in quantization to whiten quantization noise, and you can approximate it, for example, by syncing up two pseudo-random number generators at the encoder and decoder. So now I can kind of summarize our goal in math. We want to minimize the communication cost over legal encoder and decoder policies, subject to a constraint in the LQG control cost being less than gamma. If we want to impose a prefix constraint, we can think of that as applying to the encoder. Many people have looked into this problem, and I'm not going to make an exhaustive attempt to cover all the literature. The work I'm presenting today follows a line of research originally by Silva et al. In 1. For scalar plants, they derived a lower bound on the prefix-free bitrate per LQG control cost trade-off. We refer to this and other sorts of lower bounds as rate distortion formulations. In the same paper, they designed a dither quantizer and a lossless source encoder that could nearly achieve this lower bound for scalar systems. It's notable that the data compression architecture they use to demonstrate this required that the quantizations be encoded with a time-varying lossless source codec. Tanaka et al. Extended that rate distortion lower bound to MIMO plants in 3. It works out to be a numerical optimization. Likewise, they extended the achievability approach to MIMO plants in B2, but again, this required time-varying lossless source coding. More recently, Castina et al. Developed a looser but analytical bound that applied to non-dither systems. In the same paper, she developed an achievability approach that is, to my knowledge, the first provably tight upper bound that does not require dithering. The performance is about the same as in prior work, but it does, again, require time-varying lossless source codes. People have also done work on fixed-length approaches. Most of the prior work uses demonstrated achievability, that is to say, the upper bounds on the bitrate LQG cost trade-off proceeds like this. First, you find a lower bound, which leads to a hopefully tractable rate distortion optimization over some policy space. You're then going to use the solution of that optimization, really the minimizing policy, to come up with your encoder and decoder design. You're then going to analyze it and compare the achieved bitrate to the lower bound. We're going to follow a similar sort of approach here, but with an emphasis on that third part. I'm going to walk you through the first two steps when I discuss the specific quantizer design we're going to be talking about today. But first, I'm going to go over the general path taken in the prior art to analyze the quantizer designs that they've come up with. First, note that without loss of generality, we can decompose the encoder sensor and decoder controller modules into sort of two-step processes shown on the right side of the screen. The encoder can be decomposed into a randomized quantizer, which produces an output called a quantization on some countable set, followed by a lossless encoder, which encodes that quantization into the code word. This lossless encoding can generally be aided by all the random variables whose realizations are known at the encoder. Likewise, we can assume that the decoder contains a source decoder that recovers a quantization from the encoder exactly. The quantization is then fed into another potentially randomized reconstructor, which produces the control input. In the prior work, when people talk about prefix constraints, generally they're referring to the weaker constraint that I mentioned, or in fact, an even weaker constraint. In all the prior work I've discussed, the bounds on the code word length go something like this. First, they design a quantizer, and let's call the output of that quantizer Q sub t. They then say something to the effect of, well, at every time t, we can build a code word A sub t by using a code that compresses the quantization Q sub c to about its entropy. This follows from kind of a standard analysis of lossless prefix-free source codes. Even if you don't have prefix constraints, the code word length is still bounded close to the entropy. Then they usually end up developing a time asymptotic bound on the entropy of the quantization random variable. Call that bound Z. Finally, they say something like this. By Cesaro summation, my average expected code word length is bounded by Z. But here's the rub. It turns out that for all the architectures I've mentioned so far and any of the architectures I'm aware of in the literature, those Q sub t's are not identically distributed. That means that generally speaking, and indeed in all the cases I've mentioned, the lossless encoder needs to be adapted with time. In particular, it needs to be perfectly adaptive in that it needs to track the mass function of the quantization process, those Q sub t's, exactly. It's also not very likely that you'd satisfy that stronger prefix constraint. So these kind of motivate us to try to define an architecture where the lossless encoder and decoder are time invariant, by which I mean they're designed once, essentially assuming that the Q sub t are identically distributed according to some fixed distribution. If I do this, I can satisfy the stronger prefix constraint without much work. However, there are some consequences in terms of the upper bounds on codeword length. So what happens if I don't adapt? Let R be a random variable on the same alphabet as the Q sub t's. Consider a lossless entropy source code designed optimally for the random variable R. If I try to encode R with that code, the codeword length is upper and lower bounded by something that's about equal to the entropy of R. But what happens if I try to encode one of the Q sub t's with the code we designed for R? Well, we'll pay an additional overhead at every time t in terms of the KL divergence between the distributions of Q sub t and R. Bear in mind, though, that the Q sub t's are actually a Markov chain. So maybe there's some kind of limiting distribution. If there is, could we design a code for the limiting distribution, i.e., use the limiting distribution as R, and then recover the same upper bounds? It turns out that for one particular architecture for minimum bitrate LQG control, we can do exactly this. The main result of this paper is that in the dither quantizer design by Tanaka et al., the quantization random variables, that's the Q sub t's, converge to a limiting distribution, which I'll call Q infinity, in the sense that the KL divergence goes to 0. That means that if you design a code optimally for Q infinity and use it at all times, that is, you use a code for Q infinity to encode Q0, Q1, Q2, etc., you can achieve the same time asymptotic bound and communication cost that was proven to hold for time varying codes in that prior work. Notably, this bound is tight to known lower bounds. Furthermore, you'll end up satisfying the time invariant prefix constraint essentially for free. So how can you show this? Well, essentially, it all comes down from analyzing the internal signals in this quantizer architecture. I'm going to first just state the quantizer design and take you around the feedback loop. Trust me, I'm not really pulling this out of thin air. There's a lot more intuition to it than I'm letting on. I'd really encourage you to look at these references if you're interested in why this quantizer works. Before we get started, I need to tell you how to choose some of the quantization architecture's parameters. K is a matrix that's just the infinite horizon certainty equivalent linear feedback control gain. The matrix C is what we're going to interpret as a linear measurement coefficient. And the parameter delta is a quantizer sensitivity, which is going to be related to the measurement's quantization noise. C and delta are to be chosen by a convex rate distortion optimization. The details are in the references. Finally, before we get going, I want to mention the definition of what's called a uniform element-wise quantizer with sensitivity delta. You can see a box labeled that in the lower right-hand corner of the slide. This is a function denoted Q sub delta that takes in a vector and outputs that vector's elements rounded to the nearest multiple of delta. Since this is like a closed loop system, I have to pick a place to start describing the signals. Let's start with these Kalman filters. Both the encoder and decoder are going to have identical time invariant Kalman filters with the effective measurement model y sub t equals cx of t plus v of t, where v of t is IID uniform quantization noise that's independent of x of t. We'll see why we get that later, but for now, just trust me. The encoder is going to make a linear plant measurement and then compute the Kalman filter innovation using its filter's predict estimate. It's then going to quantize the sum of that innovation plus the dither signal using a uniform element-wise quantizer with sensitivity delta. So the quantization is going to be a vector on the countable set of integer multiples of delta, and it's going to be equal to the rounded version of the innovation plus the dither. The decoder is then going to receive this quantization vector exactly. The decoder is then going to form a reconstruction just by subtracting the dither, which it also knows, from the quantization vector it receives. Now, there's this classical result by Zamir and Fader that says that the reconstruction error, that is to say the difference between the reconstruction and the thing that we compressed, the Kalman filter innovations, is uniform and actually pairwise independent of CE of t. Now, note that the reconstruction is also available at the encoder, since it knows what quantization was sent and it also knows the dither. Now, all the time invariant Kalman filter needs to do is recenter the reconstruction to get the effective measurement model y equals cx plus v, where that v is an IID sequence of uniform random variables. I'll also mention that the control input is certainty equivalent. It's just a linear function of the posterior Kalman filter estimate, and it can be computed at the encoder. So now I need to mention a key result from the prior work. First, this architecture attains a control cost of gamma, which was our goal. Further, as time goes to infinity, the entropy of the quantization random variables is at most about 1.26 bits per plant dimension above the fundamental rate distortion lower bound. We'll now show that we can encode the quantizations with a time-invariant codebook and nearly attain this communication cost. So our goal is to show that those quantizations defined in the top box converge to a limiting distribution in the KL sense. The quantizations are functions of the Kalman filter error processes, E sub t, and the dither sequence, D sub t. And actually, the ET-DT joint process has a nice autoregressive description. Because of this, we chose to try to work with the random process ET-DT directly. The E's and the D's are actually a first-order Markov process on an uncountable state space. We can actually show that the pair has a limiting distribution and that they converge to it in total variation in 2 steps. The first step is to show that the E and D Markov chain admits an invariant distribution. I think of the one-step transition kernel as a channel. And the idea of trying to find an invariant distribution is trying to find an input distribution to the channel that makes the output have the same distribution as the input. There are several conditions you can find in the literature to establish the existence of something like this. And we use this great paper by Ito in the references, which has lots of necessary and sufficient conditions to prove that an invariant distribution exists. So given that the invariant distribution exists, we can show that the process converges in total variation by verifying that the chain is both irreducible and aperiodic. In sort of casual language, irreducible means that for any initial condition in any set of non-zero volume, there's a non-zero probability that will end up on that set at some point in time. Aperiodicity is just like it sounds, namely the chain can't jump deterministically along a finite sequence of disjoint sets. If you write down the one-step transition kernel, which, trust me, is not that complicated, you can pretty much see that both of these conditions hold immediately. Thus, the ET-VT process converges in total variation to a limiting distribution. So are we done? We wanted to show that the quantizations converge in the KL sense to a limiting distribution. We showed that, essentially, the things that actually get quantized converge in total variation. Unfortunately, we're not quite done. Total variation is actually a weaker distance than KL divergence. This isn't quite enough to establish the thing we set out to prove. Luckily, though, for this particular process, we're able to show that for Q infinity defined in terms of limiting distributions of E sub t and D sub t, the quantization process converges in the KL sense to a limiting distribution. The key inequality we use to prove this is what's known as the data processing inequality for KL divergence, which says that if you have 2 identical channels and you put one random variable down each, the divergence between the random variables at the inputs is more than the divergence between those of the output. In English, data processing makes it harder to tell 2 random variables apart. So in conclusion, we can use a codebook adapted to the limiting distribution of the dithered quantizations, attaining a control performance of gamma and a communication cost that's about 1.26 bits per plant dimension above the fundamental lower bound. We'd also like to thank the NSF for funding us.